Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. And this is the conclusion of the lecture entitled The Heat Equation and Fourier Series. Last time, you might recall, we did a lot of progress in deriving the equations and the boundary conditions for the heat equation. And we solved them, and we found that there were eigenvalues and eigenfunctions, and they were related to the integer n. And we also found that this condition that the initial temperature at time t equals 0 throughout the entire bar was given by f of x. So you see u of x0 is equal to f of x, and we were trying to see if could we represent f of x as an infinite sum with coefficients of these eigen functions, the sine in pi over L x. And that's where we left things, and that's where we picked them up. So, if f of x is equal to the summation of a bunch of constants depending on n of sine in pi x over L, we certainly can multiply both sides by sine m pi x over L, and we get this. Now we're summing on n, and so we just multiplied by this and distributed it in on this side. But then we're going to integrate both sides from minus L to L. And over here, the integral of the sum is the sum of the integrals, even when it is infinite, because of the conversion that we have it. And we're playing a little fast and loose with that here, but this can be done. And then the integral of a constant is the same thing as the constant times that integral. So what I'm saying is that now we've reached a point where we say, oh, the summation n equal 1 to infinity of bn is and b sub n times this, so we have to evaluate this. That's a Calc 2 problem at the College of DuPage. And you might remember you used these trig identities to help you solve that problem. You also use the fact that the sine squared of theta is equal to 1 minus the cosine of 2 theta all by 2 as well. So anyway, this was the integral that we had to evaluate, and I make a note here that this is an odd function and this is an odd function, and so if I take the product of two odd functions, I get an even function, and so I can say that this integral is the same as 2 times the integral from 0 to L of that expression dx, and sometimes that's easier to compute. So anyway, we only have two cases after you think about this for a while, and that's going to be what happens when n is equal to m. Well, if we do that, then we will have the integral from minus L to L of sine squared of this argument dx, which is 2 times the integral from 0 to L of that. And now we use the trig identity that I talked about. This is going to be 1 minus cosine of 2 theta all by 2, and that 2 will cancel with this 2 nicely. When I integrate 1, I just get x. When I integrate the minus cosine, I get this expression. And you see this is the change of variable, so that's the constant that we get. This is a definite integral, so I substitute L and 0 in. And when I do that, I get this minus this. And this is always equal to 0, so this is going to just be L. So you see, if n is equal to m, we just get L. Now, if m is not n, then what happens is we multiply these together, and we can still do this even and odd function thing here to get 2 times this. But now we are going to use the trig identity that I showed you on the earlier page. This times this is equal to this minus this. But you see, this is just integrating cosines, and we have to do a little bit of change of variable. But if we do the change of variable, we will get sines in both of those cases, and we'll evaluate those at L and 0. But what you want to notice is when you're evaluating these, and by the way, you see that's why n couldn't be n because you are dividing by it, you get integer multiples of pi for the argument of the sine, and both those are going to be 0. So you see the net of all this is, if n does not equal m, it's 0. So what? Well, that means that this integral that was the unknown that we needed to figure out is going to be L if n equal m, and it's going to be 0 if n does not equal m. So you see this integral is going to end up being just bm times L. Everything else will be 0. And I can solve for bm, and I get bm is either equal to this, or it could be written this way. We found out what those coefficients would have to be. So to summarize, if you want f of x to be equal to the summation of bn sine of n pi x over L, and you want to find out what those are, these are the coefficients that you have to have. And such a thing is called the Fourier sine series for f. Let's look at an example. So you want to find the Fourier sine series for f of x equal x on minus L to L. Well, you just compute the coefficients. So we plug in, we have x here. And this is going to be integration by parts. You should check this arithmetic. But this is what you get. And you get this expression for your coefficients. Now, the sine of n pi is always going to be 0, and the cosine of n pi is going to be minus 1 to the n. And so you see these coefficients can simplify quite a bit, and we can say bn is really equal to this. And so the sine series then for x is equal to 2 over L pi times the summation n equal 1 to infinity minus 1 to the n plus 1 over n times the sine of n pi x over L. Here's another example. Find the Fourier sine series for f of x equal 1 plus x squared on this integral. Now here you have to integrate twice, but you use the same formula, and you end up with a messier coefficient. But again, it can be done, and we found the Fourier sine series for that f of x. You can even do this for a piecewise continuous function. Here you get L over 2, and here you get 1 minus L over 2, or excuse me, that's x minus L over 2, and it breaks at the point L over 2. So what you're going to do is you're going to integrate that, but you see you break it into two integrals, and you evaluate them separately. Again, you should go through and check some of these calculations. But when you put them together, you get this is the Fourier sine series. Now you might think this is always 0, but you see sometimes even cosine is, sometimes n is even, sometimes n is odd. And so you have, this is actually the most convenient way probably to write those. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.